Hello students, today we are going to explore a new experiment about the beam structure. So a very simple case of two-dimensional beam with it simply supports. So one hinge support at one side and one roller support at the other side. And there are different type of loading scenario possible, like point load, point rotation, distributed load. In this experiment, we limit the scope to a simply supported beam with one single point load. So that point load is exerted in a eccentric way. So that means the load is not exerted in the middle. So we know that when a beam is loaded, there will be some internal forces developing inside. So here we are showing an illustration for the case when the beam is loaded in a symmetric way. So in this way, the derivations are easier and formulas are more standard. But when you do the loading in an eccentric way, so the load is not in the middle. A beam with a span of L has the loads exerted in the distance of A and B, which are not equal. And then you know how to find out the bending moment and shear forces, which are some kind of the internal forces. Bending moment is responsible for changing the curvature of the beam, and shear is a tendency to shear off, and that develops in the transverse and shear direction at the same time. The normal forces due to the axial, less important. In this case, these are not being applied. But one very important thing is, in order to comparison whether moment or shear are critical, you have to introduce a new parameter which is called stress, and either normal stress to be just imagined by axial displacement, shortening or lengthening, and the shear stress, which is a scissor effect. So once you convert the moment and shear to the stresses, they become comparable, and then you can make a decision which one is more critical. But unfortunately, there is no way of measuring stress directly. So the only way you can measure stress is by either measuring strain or by measuring deflection, none of which are a part of the curriculum for this subject. And in this experiment, we are not using strains, but we are using deflection. So I just try to give you a very brief overview of what displacement is, how this can be used to relate or to estimate the amount of the stress inside the beam, which is the objective of this experiment. So in another word, you are trying to find out stress experimentally, but because stress is not directly measurable, you have to measure deflection. So let's start with what deflection is. So here the parameter lowercase v, that is used to describe the changes of the vertical displacement of the beam. So the dark line is the deformed configuration, the thin line is the undeformed configuration. So every x has its own vertical displacement. So this thick line is, in some textbooks, is called the elastic curve, and that is very straightforward for us to measure v of x. So here we try to measure something easily measurable, something like deflection, maximum deflection, deflection at some sample points, and then all these measurements together with the slope of the beam at the start, the slope of the beam at the end. So we call this theta A, which is the tangent to the elastic curve at the beginning, theta B, which is the tangent to the elastic curve at the simply supported in the right hand side end. And if you have the measure of either maximum deflection, deflection at few points, and slopes. Then we can analyze, find out indirectly the moment distribution. We can find out the shear forces, and also we can estimate the amount of the stress given that the cross-sectional geometry of the beam is given. So in this document, this Excel page is a simulated version of the simply supported beam for two cases of symmetric loading and eccentric loading. I have utilized the formulas from the relevant formula from the accelerating material and just use them as a formula here for a beam of length L, and then these properties. Just here it has been assumed that the external load P is 2.5 kilogram, which is larger than the real load you will be using in your experiment. And as you can see that the simulated run would provide the displacement as a negative number, so 0 for the reaction at the left hand side. It gradually becomes larger, and the maximum value of the deflection for that point is something like minus 17.75. that is taking place right in the midway. That's for the symmetric load. And for the eccentric load, this is taking place just at near the middle, not exactly at the middle. That is at x equal to 560 millimeter. That's the maximum deflection. So these are just the simulated solution, just to give you an idea how much the measurements you expect, which is the instruction you have been provided mostly with the formulas which you have to use, something like reactions, bending moment measured from the right, from the left, from segment 1, segment 2, maximum bending. And just a reminder that the uppercase V is used for the shear force and lowercase for deflection. These should not be confused. And right, so once we have the expression for deflection, that is a recipe. So you are not asked to drive this relationship or even just starting that from first principle. All you do in this experiment, you use these formulas as a recipe. So, and for the loading case provided, you can find out where the maximum deflection is. That's x star, and the deflection corresponding to that, how much that is. Now let's go back to the experiment. So again, no need for derivation. You just need to have the formulas, to utilize these formulas to correlate the measured values, which are v of x and theta a, theta b, and how to correlate these to the load, and eventually how to correlate them to the bending moment, how to correlate them to the stress, axial stress. So in this experiment, you have to do 5 type of measurement, 5 type of evaluation of the loading, external load, and then from those we will be using the internal forces and the stresses. So that is a photo from the setup. So we have a C-section beam which is resting on a simply supported on both sides, and 5 extensometers. Here only 4 are being shown. So for each you would record the x and v of x corresponding to each, and these data can be used to make a curve fit, something like 3-order polynomial or higher, and that can be used to smooth your measurement and to estimate the theta at the beginning, theta at the end, and also to find out the maximum deflection, because the maximum deflection is not necessarily one of these 4 or 5 measurements that could be outside these. And then when you make a curve fit, that easily lets you to find the maximum one. Alright, so This is the geometry. You've been provided the geometry. One important calculation you have to do is free body diagram, find the reactions, and also you find out the second moment of area for that cross section. And these are the material property that's made of aluminum 6000 series, and that is heat treated as T6. So the Young modulus corresponding to that is provided. And central load 2.5 is too much. Maybe we go with something smaller, and that is I provide you with a eccentric proportion numeric value for A and B such that you know, but in this case L, the total length of the beam, is 1 meter. And then so if you are just interested, there are some readings here how the loads can be related to the other internal loads such as shear force, bending moment, and also the elastic curve and the deflections. But these are just background reading. So there are differential equations between all these variables: distributed load, shear force, bending moment, and displacement. But these are not essential for what you do. You just follow the formula. And the other techniques, this is all background information. Some web calculator, you can simulate any beam and finding their behavior under the load in case if you want to verify your hand calculation. And if you want to have further detail where these equations are coming from, at the end of this document you've been provided with some excerpts from Timoshenko, where he was one of the first people derived at that relationship for simply supported beam. The other document, this is just all for getting you familiarized with the experimental setup. When you are writing your report, there is a template. So in this template, you provide the group details, and then the symbols are being introduced, the units. So you read this one, making sure what are each symbols in the formula sheet in the document I'll show you. So you start determining the cross section property. You know, for a composite section like a C section, how to find I value. If you want to verify that, this is simple. You simply go, all you have to do is you go to the tool and then evaluate section properties, and then with this section you simply pick that is the cross section where the bending is taking place, and when you do the recalculate, it calculates the centroid and I with respect to the XX. This is the number you're looking for, then the unit is millimeter to the power of 4. So this is just for the verification purposes, because I is a critical parameter and you want to make sure you get this right. So getting back to the report template, so here you include your calculation of I, make a free body diagram of the simply supported beam, and for the loading case provided you find the reactions at A and B, and then you plot the shear force and bending moment diagram based on the provided data. And then from extensometer you repeat the loading 3 times and record the measurements and put the average for each measurement here. So X and V corresponding to each measurement. X0, V6, they belong to the supports. So practically you measure between V1 to V5 and X1 to X5. And also you have to measure theta at the beginning, theta at the end. So either you can do this by a mobile application where the inclination can be measured after the loading, or you can obtain this by curve fitting. So inside the Excel, once you have the data, you can fit a proper curve to it, and from that curve the slope at any point can be easily calculated. So once you have this, now you bring your data into the formulas. So to correlate or to separate the deflection and the position, we have produced a condensed function. Psi can be called shape function. So refer to the formula book to find out how psi can be defined in terms of symmetric loading and asymmetric loading. Write down your psi functions here, and then for every measurements you already have measured average VI, so include your psi corresponding to each case in here, excluding the start and end point. And then here just using maximum deflection, that's one way of estimating external load. So you already know how much the external load is, so this formula is an inverse way of calculating the applied load P, eccentric load P. The second way you can find that P is by using the formula and the measure theta at the beginning and theta at the end. So they made two more techniques for estimating inverse estimation of the external load P. And then you do a least square using the psi function at 5 measure points. You use that linear relationship for a square least square, and from a slope of this line you should be able to also estimate P, external load. Now you have 5 different techniques, include all of them here, or 4 different techniques, include them here. Make the average, standard deviation, and compare them with the real load and error. So once you have all this, and now you can go and pick the maximum value of the bending, and from this cross section you have to identify which point. This is the flexural formula which correlates the bending moment to the normal stress. So from this provided cross section you have to decide which one of these extreme points, either at the top or at the bottom, which one develops a larger normal stress, and that is also a part of the report. And once you have all this completed, you make a summary of the result, a table summary of the result. You do the discussion and conclusion, and these are the references in case you want to read more. And also the rubrics, you can access the rubrics for the marks from the canvas, and these are just the itemized points for your rubrics. I hope you find this recorded video useful for doing the experiment. This experiment is an important part of this subject, 10 percentile out of 100. So please make sure you go through the details and complete this report on time. And any question, like usual, send an email to me. Thanks very much for listening to this video, and take care. Bye for now.